Hello everyone, welcome back to Tanisha's Concept Corner. So, we were doing chemistry chapter D and F block elements, where in the last class we did till this part, the oxidation states and these two questions. So, now let us start with trends in the M2 plus M standard electrode potential. So, what is happening here? This is 2 plus, and if nothing is written, it is 0. M means metal. We are talking about transition metals over here. So basically, this is reduction. It will take electrons and reduce to M0, because whenever positive charge is there, that means there is lack of electrons. If negative charge is there is extra of electrons. So what is happening here? Lack of electrons is there. It will gain 2 electrons and become normal. So what are the trends we are observing when it comes to the transition elements? So let us see here. There is graph given over here for 3D elements. Scandium is not given over here because we know its oxidation state is only +3. So where will +2 come from? Over here last class we have discussed their oxidation states. Scandium is only +3. So because +2 state is not there, we are not discussing about scandium in this trend. So as you can see, gradually it is increasing, but you can see some unusual trend over here because suddenly it decreased over here. Again it is increasing, but here again for nickel it is supposed to increase, again it has decreased. And then for copper it is literally positive electrode potential. So we will discuss about why this unusual trend is there. But first let us understand this column. So generally what we have to do first is to form the metal +2, that cation, what we have to do? First atomization enthalpy, otherwise sublimation enthalpy we are giving, so that we get that particular atom in its gaseous state. We want that one atom. We don't want it to bond with anything else. Isolated atom in gaseous state. So either atomization, otherwise sublimation. From solid to gaseous state you can get. Ionization enthalpy. Obviously, for +2 state, you have to remove one electron, then you have to remove the other electron. So, first and second. For first time, you're using this much energy to remove one electron. For second time, you have to obviously give more energy, because if one electron is gone, that proton can hold the less number of electrons more efficiently, more forces of attraction, more stronger bond. We have discussed this also. So, second ionization enthalpy will be more. After giving that energy, we are actually dissolving in it in a solution. Then we will say that as hydration enthalpy. Whatever gaseous atom, now it became a cation, it will get into the solution. Now this is negative. See, till here this is positive. We are providing the energy to these atoms. Now they will release the energy. This is very important because if they are not going to release energy, they won't be stable. As I have already told, nature always wants to release energy and become stable. If it is having more energy, it won't be stable. So, this much of energy we have already provided. Now, it must release energy to become stable. That will be ensured by hydration enthalpy. When you put it in water, it is kind of forming a bond. So, it will release energy and it will be negative. Whenever bond formation is there, there will be release of energy. That is the primary reason why atoms are bonding in the first place. They are reacting and forming bonds only because they will be able to release energy and become stable. And these are the electrode potential values. Already I told you, if electrode potential values are more negative in the first class, if they're more negative, they will easily lose electrons and become a cation. But here we are talking about gaining electron. So if it means more negative, if the electrode potential value is more negative, you can easily say that this M2 plus won't easily convert to M0. Generally, if more negative is there, they are having the ability to lose electrons and become cation. But here I am trying to give them electron. So that's why if you're seeing this graph from M2 plus to 0, if this is talking about reduction, if it is talking about gaining electrons, if you see more negative value, like towards the more down, towards more left on the number line, that means understand they have the ability to lose electron, they don't have the ability to take electrons. So from this we can easily understand titanium, vanadium, which are more towards the left of the number line, like this is 0, this is more towards the left of the number line, meaning they are good at giving electrons than taking electrons. And gradually it should keep increasing, but for manganese it is not. If you're seeing lesser value, understand that less preference, that it doesn't want to convert. If you see high value, understand that it wants to convert. Okay, less value because whenever this is a stable state, obviously it doesn't want to convert. When it is already stable and comfortable, why would it want to gain electrons? That is what is happening with manganese. If you see the electronic configuration again, for manganese, if you see 2 plus, again this entire thing is argon as I already told. So it is argon electronic configuration, a noble gas configuration, more stable. So for 2 plus, it is comfortable and happy, so it doesn't want to convert. That's why manganese is going down. No need. I don't have that much interest in converting. Generally it has to increase, but it is going down because of the noble gas configuration and stability it is already having. Same with zinc also, it is coming down. For copper, it has raised so much, and for zinc, again, it is dropping down below. Why is that? For zinc, also consider 2 plus, d orbital completely filled. So, if you consider d orbital, it is being completely filled, more stability is there. That's why zinc doesn't want to prefer. So, if they say for manganese and zinc, why the values are really low, according to the trend, it should be increasing, but they're low. If they ask that, because plus 2 state meaning 2 electrons gone here, 2 electrons gone here, here 5, d5 meaning half filled, it is more stable. Here 10 meaning completely filled d orbital, it is more stable. So that's why they don't want to take electrons and convert back. Then one more thing is for nickel. Nickel, it should actually increase a little bit more than cobalt, but it isn't. This is because if it is in plus 2 state, hydration enthalpy is more for it. So whenever it is releasing more energy, automatically it will become more stable. That's why highest negative because it's releasing exothermic, highest negative hydration enthalpy, meaning it will release more and more energy and it will become stable. So if it has released more energy and stable, why does it want to again gain back electron and convert? So that is why it is comfortable in being plus 2 state. If it is comfortable being in this state, it doesn't want to convert. Then you will get the less values. Then you're like copper. Copper, though, it's literally going to positive only. Why is that happening? Generally, it's not even liberating H2 from acids. This means that copper is always ready to take electron and convert back. Generally, copper should be able to give electrons to liberate H2 whenever it is reacting with acids, but it doesn't, because it wants to take electron and fastly convert to copper. Because in copper 2 plus, I said right, ionization enthalpy we provide so that we can take away the electron, but again hydration enthalpy which is there, it should be able to release more energy, at least little more than whatever we have given, or same amount. How much ever energy I have given, that should be given out so that it won't have energy, it will be stable. But it is not balanced here. How much ever ionization enthalpy I am giving it, that much or more than that should be released in hydration enthalpy. But no, less than that is released in its hydration enthalpy. So if I am giving suppose like 300 joules of energy to obtain copper 2 plus, in hydration enthalpy 100 or 200 is only released. Extra 100 is there. If 200 is released, let's say a 300 I've given, 200 released, extra 100 is still there in this 2 plus. So it's again not stable. It will realize, oh, okay, I have accepted to give away the electron, but I'm not stable. So that's why this electrode potential is positive, so that it wants to gain its electron back and become copper again, so that it will become stable and it won't have that extra energy. So that is the reason for this unusual properties. For manganese, because D5 half filled. For zinc, it is D10 full filled. Full filled d orbital, half filled d orbital, already stable, they don't want to convert. For nickel, it is the hydration enthalpy being more. If it is releasing more energy, it's already stable. So again, it doesn't want to convert. For copper, it is high. It wants to convert because hydration enthalpy is not being balanced. How much ever energy provided, that much is not being released. So extra energy will be stored in it. Hence, it will be unstable. So these are the reasons they could ask in the questions. So over here, they're saying in this question, Cr2 plus Mn3 plus both are having D4 configuration. But this is a reducing, meaning it is a reducing agent, meaning this will get oxidized. If this is reducing agent, this will get oxidized, meaning it has to lose electron. And for manganese 3 plus, oxidizing agent, meaning this will get reduced. This will get reduced, meaning it will take electron. Why? Both of them are having same electronic configuration. Why is this happening? See, Cr2 plus is reducing agent where it is going to give away one electron. So 4 were there, it will give away one electron and become 3. Now this is something called as half filled T2G level, which is more stable. For now, always just remember, whenever you see this D3, this is half filled T2G and it is having stability. Just like half filled D orbital is 5, completely filled will be 10, and 3 is half filled T2G. Now we don't have to go in depth about this because we will see it in the further chapters. So for now, just understand this. Okay, so why is it so eager to give away one electron? Because it will achieve 3. This is more stable. But for manganese, it is so eager to gain an electron. Whenever you gain an electron, you get a negative charge. So remember, 3 plus is there. If it is gaining one electron, it will become minus 1. So 3 minus 1 is 2. Whenever you're gaining electron, put minus symbol. 1 electron is gained, meaning minus 1. So it becomes 2 plus, meaning it is gaining 1 electron. 4 was there, 1 electron will come, 5. So half filled, extra stability. We already know this. Now, already discussed, copper is positive. What is the possibility? They already gave the hint also. High atomization enthalpy, high ionization enthalpy, but hydration enthalpy, when it comes to releasing energy, it is not releasing. Then extra energy stored, it will be unstable. That's why it wants to convert back to copper. More preference for converting back. These are the reasons that I have already told. Now let's see, just like we have seen M2 plus to M, now we will see 3 plus to 2 plus. Over here, you're gaining 1 electron. If you gain 1 electron minus 1, it will become plus 2. Now, for scandium, low value, meaning whenever less value is said, it won't convert easily. That is what it means. Low value meaning it likes this state more. So it doesn't want to convert. Why? We already know scandium 3 plus is noble gas configuration. If you see the electronic configuration, we can see it here. So this is 2 electrons will be gone, 1 electron will be gone because 3 plus. Then what is this? This is nothing but argon noble gas configuration. It will be more stable. So if it is plus 3 state, because it's more stable in plus 3 state, it doesn't want to convert to plus 2. So there will be low value. Now for zinc, highest value is there. Why? Because as soon as it is going to convert to plus 2, it will have 10. Already seen. Plus 2 meaning 10. Completely filled d orbital, more stable. Always check where it is more stable. If it is stable over here, low value, it won't convert. If it is stable over here, more value, it will convert. Same with manganese also, high value is there because D5. Plus 2 state meaning, for manganese plus 2 state meaning D5. Half filled, more stability. Which is preferred? M2 plus is preferred. So high value will be shown and it will easily convert. Now low value for iron, because again it won't convert. If it is low value, it is not going to convert because 3 plus which is there, this is D5. It is already stable over here, so it will have low value, it won't convert. For iron, if you see 3 plus, 2 will be gone here, 1 more should be gone from here. Always remove from 4s first because this is the outermost. 2 will be gone here, 1 will be gone here, meaning 5 will come. So half filled symmetry, then more stability. If it's already stable over here, it is not interested to convert to 2 plus. That's why low value. Then for vanadium also related to stability, because if I talk about comparatively low value for the V2 plus, because this is half filled T2G level. Again, half filled T2G level is actually stable. We have learned whenever D3 is there. So that's why if it is not interested to convert, it won't. But over here, we have to see which is the more preference. V2 plus is the more preference. So it will convert comparatively low value as compared to manganese and iron, because this is D5. This will be comparatively less than this, but still it will be high enough for achieving 2 plus, because it is more stable over here. If you see 2 plus, For vanadium 2 plus 3 is coming. Always remember D3 meaning half filled T2G orbital, which will be stable enough. So this will prefer this more, so it will convert. It will show comparatively low value when compared to iron and manganese and all who are having this, but generally high value only. Now when it comes to stability of higher oxidation states, now when there are higher oxidation states like 7 electrons, 6 electrons they're losing, then some other element should come and give electrons to that also, right? Or they have to share electrons and form a bond. So what elements? Most of them will be halogens. So if they are asking which elements are coming, they will be halogens. But the mostly two elements that we will be talking about is fluoride and oxides. Fluorine and oxygen will mostly are going to cover the higher oxidation states. In few scenarios you can see halogens also. So for titanium, if 4, suppose its oxidation state is there, 4 valency is there, meaning X is halogen, fluorine, chlorine, bromine, iodine, anything can come and form bond with it. For vanadium, fluorine came. See, 5 is the oxidation state for it. It is higher oxidation state. So fluorine will come and form the bond. For chromium, 6 is there. Fluorine will still come. Plus 7 state for manganese is not represented in simple halides. But over here, when oxygen and fluorine both are coming, you can see the plus 7 state. But generally in simple halogens, just like that, chlorine cannot come and form. Because when it comes to these chlorine, bromine, iodine, these kind of halogens, they are having more larger size, and compared to fluorine, they are having less electron negativity, so they won't easily grab electron and maintain the bond strong. That's why most of the cases oxygen and fluorine only is coming and forming the bonds. Now beyond manganese, no metal has a trihalide except these two. For iron and cobalt, you can take fluorine, chlorine, bromine, iodine. 3 state will come, but for other metals, it is actually not, because if 3 plus state, if you're taking for other metals, if you see the electronic configuration, it is not much stable. For Fe though, plus 3 state is stable. For iron, if you see plus 3 state, here 2 gone, here 1 gone, 5. So half filled and it will be stable. But for others, if you take plus 3 states, here 7 electrons will come, it won't be much stable. So that's why you can't see trihalide. For cobalt also plus 3 is 6, but it's comparatively fine. It's still stable enough. So for cobalt and iron, you're able to see plus 3 states trihalide, but other than that, they will not be that stable, so they won't prefer. The ability of fluorine to stabilize. Now, why mostly fluorine is the one? Because of high lattice energy and also higher bond enthalpy. When it comes to fluorine, high electronegativity is there. It can pull the electrons. It is of smaller size, so it will form a strong bond. Like metal which is there, it is highly electropositive, and fluorine is highly electronegative. Positive, negative, more attraction will be there, more stronger bond can be formed. So high lattice energy, high bond enthalpy, more energy should be given to break them. If they're more stronger bond, more energy should be given to break them, so they won't easily break, meaning they're strong bonds, they're good bonds. So that's why mostly with fluorine only, these higher oxidation states they are forming. For vanadium 5, for chromium with 6, they are forming these. So again, vanadium 5, generally this is not undergoing hydrolysis. If you take any other halide, if you're going to put it in water, oxygen is coming in and they're forming like this oxahalides. Oxygen and halogen coming with the metal, oxahalides. But when fluorine is there, this won't happen. Fluorine forming like a very strong bond, it is not going to allow oxygen to come in between or any other hydrogen, because hydrolysis H2O meaning hydrogen to come in between. It's already strong bond because of high lattice energy and high bond enthalpy. And one more thing, it's again highly electronegative. So it is like pulling the electrons, it is forming a strong bond. Any kind of in H2O, oxygen and hydrogen are not very much capable to remove this person or replace this person. Strong person this is. So that's why in actually 10th grade, no, in 11th grade, we have studied in disproportionate reaction, fluorine is not undergoing that because it is not undergoing hydrolysis because of high electronegativity. All these things we have studied, why we can't obtain it from the ore. So that's why this won't go under hydrolysis, any other halides will undergo. And one more thing also, whenever lower oxidation state is there, fluorine will not come. Here +2 state is there, meaning only chlorine, bromine, iodine will come. Why? Again, fluorine wants more electrons. It is electronegative, meaning it wants to pull more electrons. If 2 electrons are only there, it won't be satisfied. It will say, I don't want. If I want the deal, you have to be at least 3 or more than 3. So like that, it is a greedy person. You say, no, we want more money. So like that, it needs more electrons to pull and uh, become stable. So it won't fall for these small number of oxidation states. Same thing for copper with any halogen also. Here also only for chlorine, bromine, iodine, not for fluorine. +1 state though, fluorine is not coming. It's like, no, you have very less electrons to offer, I am not gonna come. So it won't come. But for copper 2 plus, it is coming, and all the halogens will come except iodine. For here, fluorine won't come. Here also fluorine won't come. Here, everything else will come except for iodine. Why? Because copper +2 state oxidizes. -1 is there, meaning it is having one extra electron. Oxidizes meaning oxidizing agent. It will reduce, so it will take that electron. Isn't it? One extra electron is there, it will take and liberate of I2. So Cu to I2, actually you can cut this off. 2 ones are 2 ones are. So Cui. So always Cui is forming, Cui2 is not forming. That is what they meant. +2 state with iodine, it is not forming, meaning they're expecting to form Cui2, but it is not forming +2 state because Cui only is forming. It is giving off electron. I mean, it's taking the electron because one extra electron is there and liberating of I2. Here 2 ones are 2 ones are, that simplest ratio Cui you can write. So don't get confused here. 2 is there, +2 state is offered. +2 state it is not offered. For Cui2 is not formed. Then again they're telling Cu plus is undergoing disproportionate reaction and forming Cu +2 and Cu. Why is that? Generally it is not stable. Whenever you take any aqueous solution, if you're considering copper plus, it is disproportionate reaction, meaning again when one element is having like at least 3 oxidation state in one particular reaction, it will undergo reduction also, oxidation also. So here it has lost one more electron, got oxidized. Here it has gained electron and it has reduced. This is +1, when nothing is written 0. So 1 to 0 is reducing. If electrons, if you can see here 1 and 0, the oxidation state is getting less, meaning it means it is reducing. So 1 to 0 oxidation state reduced, so this is reducing. And 1 to 2 oxidation state increased, meaning oxidation. So one element only is undergoing oxidation also, reduction also, that is disproportionate reaction. Now why is this? Because copper 2 plus is having more stability because more negative hydration enthalpy. It will release more energy so that it will be enough for the ionization enthalpy that you have provided for the copper. How much ever energy you have provided, that much is released over here. So it will become more stable as compared to Cu plus. So it is little bit stable because it has released some energy compared to Cu plus. So this Cu plus will be like, I want to become stable, so it will get into this state where copper also is stable. This is also little stable because it has released energy because of more negative hydration enthalpy. Hydration enthalpy is always negative because energy is being released. Now I have talked about two elements. Fluorine is able to bond with the higher oxidation states and forming really strong bond. Similarly, oxygen can also do. In fact, oxygen is way better than fluorine because it can form multiple bonds. It can offer like 2 pairs of electrons. Like here also if you see MnF4. For fluorine, maximum 4 is the oxidation state. Generally for manganese till +7 it is there, right? But fluorine till +4 it is already happy. It is like, okay, till this much it's fine. But oxygen is able to even take +7 state also. Higher oxidation state you should be able to satisfy. For manganese +7 state, oxygen is able to take because it can form multiple bonds. Like over here, 2 manganese are there, 7 oxygens are there. So it will be one bridge kind of thing. If you see, this is one manganese, this is other. So oxygen over here will be providing for these both. And again extra 3 oxygens can be written like this because 7 oxygens are there. Mn2O7. So it is able to bond with both of them. So it is able to form multiple bonds. That's why more than fluorine, this is more capable. And also higher oxidation number in oxides coincide with the group number. Whatever oxidation state is highest for that element, oxygen is able to take. For scandium +3, that is only one, but is highest one for scandium is +3. So oxygen is like, okay, fine, no problem. For manganese is +7, okay, fine, no problem. Oxygen will still accept that +7. But for iron, when it comes more than +3, it is not able to go. Iron will show +6 state also, but for more than +3, it is not able to go. Though +6 for like temporary amount of time, it is formed in like a alkaline medium, the base kind of medium. But again, quickly it is decomposing back to +3 state only because +6 state is not that much stable. So oxygen is not able to stabilize that many electrons when it comes to iron. So that is why till +3 only maximum it is able to take. Then besides not just oxides, oxa cations also like O2 plus. Cation meaning positive charge is there, no? Suppose vanadium 5 is there, it has to be stabilized, meaning VO2 plus is coming. Suppose vanadium 4, fourth oxidation state is coming, meaning oxygen with 2 plus charge, cation plus positive charge it is coming and it is able to uh, stabilize these elements. So if you see over here also, two oxygens, oxygen ka general oxidation number is -2. So -2 into 2 is 4. If you are getting confused, I'm just helping to find the oxidation states. Don't just see this number and decide of iron is +3 or not and all that. You have to sometimes calculate over here. How is vanadium 5? Generally in redox chapter, how did we calculate in 11th grade? Like that. So oxygen -2 meaning 2 2s are 4 -4. Vanadium we don't know, so it is plus x is equal to +1. So it is -4 because oxygen is generally -2 and two oxygens are there. So -2 into 2 is -4, and for vanadium we don't know, so let me think it as x. It is equal to, they have given uh, +1, how much ever charge is above. If nothing is there, it should be equated with 0. So this is +1. If 4 is going this side, it will become positive, so x will be 5. So like that you can calculate and check. And already told how oxygen is more capable of fluorine because its ability to form multiple bonds. And tetrahedral, generally this any metal might be there, 4 oxygens, any +4 state might come with any amount of charge among them. So over here, whenever 4 oxygens are coming and forming bond with any of our transition metals, their oxidation state may be anything. It will depend upon this number. Like over here it was +1, so that's why vanadium was 5. If it was something else like 2 plus, then again while calculating you will equate it with 2, and again the oxidation state for this metal will change. So for these kind of stabilizing formula, if it is there for these metals, it will work. For vanadium 5, for chromium 6, for manganese 5, again for manganese 6 and 8. So if they're coming with that, this is 7, sorry, not 8. 8 is not there, till +7 is only there. So with that kind of oxidation states, if they're coming, oxygen is able to stabilize in this format. Now they're asking one question over here saying that this is the how the oxidizing power is increasing. For first, this is actually manganate ion, which we will learn further also. So this is there, then this, and then this. This is having more oxidizing power than these two. Why is that so? So we have to give reasoning. They have simply mentioned increasing stability. How? If we have to check, if you calculate the oxidation state over here, 4 oxygens are there, so it is basically -8. 4 oxygens, and it should be multiplied with -2. -2 is the oxidation state for oxygen, so it will be -8. Manganese value we don't know, so plus x is equal to -1. That's what is given over here. -1 is given, and 4 oxygen, so -2 is the state for oxygen. -8 plus x is equal to -1. Send 8 over here. 8 minus 1, x is 7. So they have asked oxidizing power. Oxidizing power meaning their ability to reduce. Oxidizing agent is always where they are basically taking electrons and reducing. Oxidizing agent meaning they have to get reduced. If they have to get reduced, they have to take electrons. Now sure, this will take electrons. Why is this taking electrons? If it is taking like 3 or 4 electrons, what will happen? For example, it is taking 3 electrons. If it is taking electrons, minus sign will come. So if it is taking 3 electrons, minus 3, then you will get plus 4 state. Manganese has that state also, no, so fine. And if it is say suppose taking 4 electrons or 5 electrons, so let us say it is taking 5 electrons, then minus 5 will come, then you will get plus 2 state. So the thing is that if they are going to take the electrons and they're going to reduce more oxidizing power, so manganese is showing the ability to get reduced to these oxidizing powers. So why is it preferring to this states? Because if you see plus 4 state for manganese, if you see plus 4 state, first these 2 electrons will go, then from d orbital another 2 electrons will go, so 3 will come again. D3 is there meaning half filled T2G, which is stable. Over here, if it is preferring plus 2 state, again if it is 2 electrons gone, half filled. So that is why it is showing more oxidizing power, the ability to get reduced, the ability to take the electrons and reduce its oxidation state, so that it can achieve either half filled d orbital or half filled T2G orbital to become more stable. So this will be firstly ready to grab the electrons. So more oxidizing power, they have given the order already. Then comparatively next is chromium. Here also if you have to calculate first what oxidation state this is, 7 is there for oxygen. 7 is there meaning oxygen generally oxidation state is -2, so 7 into -2 is -14, but 2 chromiums are there, so you have to put 2x. If 2 here only manganese 1 was there, so we directly wrote x. Over here we have to write 2x, and that is -2 is equal to -2 because at top that charge only is present. So if 14 is coming over here, 14 minus 2, 12, then 2x will be equal to 12 meaning divided by 2, okay, 6 is the oxidation state. This will also grab the electrons and become +3. If it is taking 3 electrons, it will become +3, because if it is taking electrons, minus sign will come, 6 minus 3 is +3. Now why will it prefer this? If you consider +3 again over here, 6 will come, comparatively fine, okay, it will become little stable. So it is going to, so not cobalt, sorry, chromium. So for chromium, we are talking about chromium over here. So if you see chromium's electronic configuration, we got +3. So if I talk about +3, here 1 electron will be gone, again 2 electrons will be gone. So this will be D3. Again half filled T2G orbital, which is again more stable. So it will also, okay, fine, it will gain electrons and become this. So but compared to permanganate, it is comparatively less, but still it is having oxidizing power to take that electron. And for this is the least. Why is this least? Now if we have to mention, for this oxidation state for vanadium will be -4 plus x is equal to +1, it will be 5, as we have seen over here, it is 5. Now for vanadium, the oxidation state is +5, meaning 2 electrons gone from here, 3 electrons gone from here, noble gas configuration is there. So that is why it is already stable. Why would it want to gain electron? Doesn't make sense. That's why it is having least oxidizing power. Those are the reasoning. You can tell this is more stable if it is converting, this is more stable it is converting, so that's why they're taking electrons. But this is already stable, so it will not show, it doesn't want to take electron, that's why it is having least oxidizing power. Now they're telling there is this irregular variation of ionization enthalpies in the first series of transition elements. Like we expect it to be like a proper trend. Generally, along the series, if you're going to go, ionization enthalpy will be increasing only, because as you go along the period, what will happen is atomic size will be reducing, because orbitals though will be same. Here all the orbitals are same, d orbitals, s orbitals, but number of electrons keep increasing. If they keep increasing, the more forces of attraction will be there, and their bond will be stronger, so they will get smaller between these. Like this is the first orbital and this is the nucleus. If there is more attraction, this will pull towards here, towards the center, so it will become more smaller if it is getting pulled towards the center. If it is more forces of attraction is there, then taking away electron from it is difficult, so ionization enthalpy should increase in that case. But if we see 3D series, some cases it is increasing, some cases it is decreasing. Why is there a irregular trend, they're asking. So first reason you can say is because electronic configuration having certain exceptions. We know why it has exceptions also. I have told the reason, saying that this 3D and 4s are almost similar energy they're having. So electron can here, it can be here, or it can easily exchange from here also. So that's why that configuration is also little getting exceptions here and there. So if you see here, the more preference towards the half filled and full filled d orbital is there. Then what will happen, they'll become more stable. If they're more stable, taking away electrons from them is difficult, and ionization enthalpy will suddenly increase a lot. So that's why for manganese and all, they might increase a lot. If I take everything plus 2 also, for zinc suddenly it will increase because it will have fulfilled. So that is the first reason. How you can write the point as there is more stability for half filled and completely filled d orbitals, which leads to increase in ionization enthalpy. That is the first scenario. Because here suddenly one electron is going, meaning s one more electron will be there, you can easily take away, there is no problem. But here also if you take plus 1, 10 is there, it will become of difficult, suddenly it will rise. So that's why you can't expect a proper trend over here because of that one point. And one more important point is d orbital, which is not very good at shielding. We know the shielding effect, like electrons will be moving and shielding, like protecting the outermost electrons or whatever electrons over here from the nucleus charge, so that the nuclear will not be able to pull them inwards, so that they'll be free to at least get away. If they're more free from the nucleus, the easier they will come out. So if they have to come out easily, less energy will be enough, low ionization enthalpy will be enough. But the problem is d orbital is not very good at shielding. Whichever is more closer to nucleus, that will shield more. So s will shield more, then comparatively p will do less, then d will do less, and f will do more less shielding. So if they're not able to shield properly, the effective nuclear charge, that means how much ever that nucleus is attracting the outermost electrons, will become more. So if it is attracting it and pulling towards it, taking away the electron will be difficult, or this electron won't be any longer free because it is constantly being pulled by that nucleus. So because of improper shielding of the orbital, in some scenarios it might shield fine, in some scenarios it won't shield properly. If electrons are increasing, it can't shield properly. Like if in d orbital electrons are more, meaning it will be able to shield, but if electrons have less, meaning it won't be able to shield. One electron rotating can't shield the outermost two electrons. If more electrons are there, okay, they can hide that nucleus from pulling these two electrons which are there. But if there are less number of electrons, they can't easily uh, like protect the outermost electrons from the nuclear charge. So here it won't shield properly, but suddenly here it will shield properly. The nuclear charge will be keep on fluctuating. That pulling becomes less over here, the pulling is more over here. If it is more over here, ionization enthalpy is more. If it is less over here, ionization enthalpy is less. So that's why there is too much of irregular variation when it comes to ionization enthalpy. We can't expect one proper trend to go on because of all these scenarios. So I will stop here for today. Then we will further cover all these topics in the next videos. If you like the way of teaching, please like my video, and any sorts of doubts or problems or any other questions you want me to solve, please feel free to leave a comment in the comment section. And please subscribe guys. Thank you. Bye.